Hi everyone, welcome to the talk. My name is Pradeep. I work as software engineer for test and safety team at Yelp. Today I'm going to talk about how Yelp does real-time bot detection with Flink. Yeah, let's get started. For a few of you that have never heard about Yelp, Yelp's mission is to connect people with great local businesses. So in order to do that, we have a website, iOS and Android app where users can search for businesses, look for reviews, make a reservation, request a quote, and they can interact with the businesses in several ways. So in this talk, I'm going to go through overview of how Yelp uses Flink with the real-time bot detection, and also I'll talk about some of the challenges that we faced and some solutions that we adopted and the lessons learned during this process. So why are bots a problem? So bots can be a problem at several levels for a company, from resource consumption to accuracy of its generated metrics. And also, it directly influences Yelp's mission to connect people with great local businesses. Yes, there are several ways in which the bots can affect your system. Some of them are the traffic. The traffic that is received from the bots can directly influence the search and business metrics at Yelp, which brings the negative impact on machine learning models that are powering the search and recommendations. So Yelp generates revenue from ad clicks. So you do not want to charge the business owners for clicks done by the bots, therefore influencing the revenue of the company and the ad budget of the business as well. And the third part is the content that is generated by the bots. That can be ratings, reviews, which directly influence the quality of the Yelp's content. So as you can see, there are a lot of problems that needs a solutions. Now we know the problems with the bots. We need to find the right tool that solves this problem. So there comes the need for the Flink. So previously, Yelp has a batch jobs that detects these bots, but the batch nature of the jobs is not effective to catch the bots while they're active. So we need a tool that can detect bots in real time. Secondly, the scale. So we have to process around 2.5 billion events per day. So you need a tool to support this scale as well. And the nature of the bot detection job requires a huge state that needs to be maintained. So you also need a tool that can support large state as well. So with this context, uh, I'd like to introduce real-time bot detection platform at Yelp. So we think Flink is the right fit for all these use cases. Yeah. So the bot detection platform receives events from mobile and website users as well as the Yelp's backend services in real time. So it processes these events using Flink and generate classifications for each user on whether it's a bot or not. So we push these classifications into different sinks to support various use cases. I'll talk more about these use cases in future slides, but let me deep dive into how these events are consumed in the Flink. So the bot detection platform constructs user sessions in Apache Flink. So it does that by grouping users' activity based on the sessions. So Flink allows us to define a time gap between the messages, and all the messages that arrive within a period of inactivity less than that defined time gap can be considered to belong to the same session. Now, once the user events are grouped into session, so all the events are taken from that session. We compute features for these events, and then further use rule-based and machine learning-based models that would classify if a user is a bot or not based on the features that are computed. Now, so like I said, there are four phases, which is making the session windows, taking all the activities of the user that fall into the session, doing the future computation, and finally the bot classification from those messages. So yeah, this lands me into the first problem that we faced, which is the problem of ever-growing session. So a user activity can be grouped into session as users have that periodic inactivity between the events, while the bots have a continuous activity for hours, maybe days, and maybe months. So this could lead to two problems. One is your state is going to increase forever because the session window cutoff would only happen if you have a time gap between the events. So, and the other problem that you could face is you could potentially never receive a classification for a bot, as yeah, you always have that continuous activity, and the session is always being evaluated. Uh, so, so what's the solution to this problem? So what we did is we we tried to do a hard cutoff for these sessions. no matter if it's from the users or the bots. So we always truncate the sessions. Now we're doing two things here. One is we are trying to solve the problem of cutting down the size of the state, as well as we're trying to provide a classification for the bots as well, as you wanted to avoid that ever growing state. So how we did that. So from the code perspective, so we have overridden the session length trigger. So the first thing that you see is the default trigger that you get from the Flink, which is if the watermark passes the window max timestamp, you would fire and purge the session, which means the fire is evaluating the events in that session, and the purge is removing all the events from that state. So what we have added is the second part. We started storing the timestamp of the window, which is the window timestamp, window start timestamp, and then we have defined a maximum session length. So now we have the maximum size of the window. Now, if the watermark passes this maximum size of the window, we would trigger a fire and purge, which means we are evaluating the session, which is providing the classifications, and the second part is purging, which is you're removing all the events from the state, therefore freeing the state. Now, the second problem which I wanted to talk about is the inconsistency across the sessions. Now, what does that mean? As you can see, we provide classifications for every session for a single user. Now, every session is being evaluated, and then you provide classifications for every session. Because of the nature of how user uses Yelp, so the first thing is I could be searching for a lot of reviews, and I could be looking at the ratings of a lot of businesses where the activities of the in the session could be large, while if I'm looking for just a contact of the businesses, the activity of a user could be very short. So there is a large variance in the number of messages across the sessions, which means there is a potentially you could give inconsistent classifications for the same user across the sessions. So this is what you want to avoid. And also the second problem with this is it's hard for the rule-based and machine learning-based systems to adapt to this kind of variance and give a consistent classifications across the sessions. So this is also one of the problems that we wanted to solve. Now, what's the solution for this? So to solve this problem, what we did is we first analyzed the features that needs to be carried across the sessions, which means we wanted to see what are the features that needs to be aggregated across the sessions, which is some of them are like request count, number of clicks, or maybe the time spent by the user in a session. So we added a state to these features with a predefined TTL. The TTL can be hour or month or maybe a day. So you may want to carry the information of these features across the session during for this amount of time, which is the TTL in this case. Now, how this helps is that it'll not only brings the context from the previous session, but also it will help our rule and machine learning based models to tune these features for the TTL defined in this case. So that's how we solve this problem of inconsistency across the sessions, which means now you have a context of the previous sessions as well as your models are tuned to provide a good precision and recall for the defined TTL. Now we have processed we talked about some of the problems that we faced during the bot classifications. Now, once these classifications are produced, someone needs to consume it. So I want to talk about the problem that we face while consuming these bot classifications. So before going into that, I wanted to introduce how we provide the bot classifications to some of our consumers. So there are three use cases mainly for which we have three integration endpoints. The first one is Kafka. So we push all the bot classifications into Kafka. So whoever wants to consume the classifications in real time can join their stream with the bot classification stream in Kafka in a separate job, and then they can consume these. So it's more for a real time use case. The data lake use case is more for batch jobs and offline analysis use case, where if you wanted to run a batch job, maybe hourly, daily, or even weekly, and then consume the bot classifications for that week or for that hour, you could use data lake to do the join. So it's more for offline and analysis purposes, or you could analyze the bot classifications over a long period of time. The third part is also for a real-time use case where we built an API on top of Cassandra, and then whoever wants to consume these classifications through API can use that API, which is powered by the Cassandra in this case. Now, with this background, I wanted to introduce the first problem that we faced while consuming these bot classifications. So the problem is the duplicate classifications. As you can see, we produce multiple classifications for a user, which means we are classifying every session into a bot or not for each of the user. Now, which means when I join the bot classifications with my stream, I would get multiple classifications for a single user in a join window. Now, how do I consume that? Like, what classification should I pick, or should I pick any classification? Or and also as the window size increases, the probability of the multiple classification increases. Now, to to solve this problem, what we did is we suggest our consumers to always pick the latest classifications of the user in the join window, which means in a given join window, you would always pick the latest classification that you received for that user. Now, how this can be done? This can be done by using the Flink by using a row number. So you can join your stream. You can use row number, which will actually order the classifications of a user, and then it'll by the time, and then the first one would give you the latest classification of the user. So there you can see the row number is equal to one there. Now, what's the problem with this? The row number is supported only in the Blink planner, which is the default plan for the latest version of the Flink. But we also wanted to support the our consumers who are using the older version of the Flink as well. Now, so this is the solution that we have adopted to solve that particular problem. So as you can see, the first one is the event stream, and the second is the input of the user, and the second one is the classification stream, which are the bot classifications. Now, each of these streams, as you can see, there's a wrapper around it, which is a common wrapper for both of them. So which is we call it a message. Now, it helps us to union both these event and classification streams into one stream, group by user, which means the grouping by user is bringing all these events that belong to the same user in a one window. So now we wrote a custom process function. I'll talk more about the custom process function in the future slides. But the idea of the custom process function is to process all the events and the classification and pick the latest classification in that window and append that classification to each of the event streams that fall into that window. Now, from the code perspective, this is what it looks like. So we have overridden the key process function. So the process element is to process the events that fall into the same window. Now, as you can see, there can be two types of events that fall into this. One is the event type, and the other is the classification type. So the event type, we need to store all the events that fall into the window in the state. While the classification state, we just need to pick the latest classification and store the latest classification that you receive for that user. So we can order them by time, and we can pick the latest event always. So the timer service here helps us to eject the events stored in that state, which means periodically we can cut off the window, and then we can eject the events that are present in the state by appending the latest classification of a certain user. So yeah, this is how we solve the problem of duplicate classifications. Yeah. So Flink has been doing well for us. It not only helped us scale, but it effectively helped us deal with the large state. So in summary, it computes tens of millions of user sessions for us per day, and it filters out tens of thousands of ad clicks per day that are from the bots. And currently, we are at a 1 TB of a state, which is a huge state, and we have been going smooth with Flink. Thanks everyone for attending the call, for attending the talk. Hopefully, some of our learnings are helpful to you. Yeah, thank you.